So in the last video I said I would show you where to find these standard electrode potentials and how to use them and how to write down an overall chemical equation. So let me reach into our textbook and show you the table. So the first thing is it's a very big table, and I apologize for it being so large. In fact, I zoomed in on the top half because I'm not sure you could read it if I showed you the full table. The way it's arranged is that we write the reactions as reduction reactions. So some people call these standard electrode potentials standard reduction potentials. It doesn't really matter, that's just our convention. And one of the reasons is it doesn't matter too much is that when we calculate the cell potential, we take the standard reduction potential for the cathode, which is on the right-hand side, and we subtract away from that the standard electrode potential for the anode, that's on the left-hand side. So our cathode, right, is reduction anyway, so the reaction's written as is. Our anode is on the left-hand side, right, and that's an oxidation. And you might say, well, all these reactions refer to reductions. And so, yes, you're right, the chemical equation needs to be turned around. And if you ask, well, what about the voltage here? Well, if you look at that minus sign there, it's essentially turning that voltage around anyway. So everything is handled out no matter what. You don't have to ever change these voltages. Now, one interesting thing is, how do you possibly figure out what these two things are if you can only ever measure one cell voltage? And it turns out that we have to build a convention in. We have to agree that one of the electrodes has an assigned voltage of, say, 0. And then if we make it, say, the anode, any cell voltage we measure is exactly equal to the cell voltage of the cathode. And what we do is we pick on hydrogen and we say that a standard hydrogen electrode gets assigned a voltage of 0. And then if we ever build a cell with that standard hydrogen electrode on the left-hand side as the anode, then essentially you're subtracting 0 away from this. So obviously the cell voltage is exactly equal to the standard reduction potential. So let me show you the hydrogen electrode and show you how it works. So here's a picture of the standard hydrogen electrode. And so we basically bubble in hydrogen gas at a pressure of 1 atmosphere into a solution that's essentially 1 molar like nitric acid or 1 molar in hydrogen ions. And so the hydrogen ions and the hydrogen gas can undergo a redox reaction. We normally have a inert surface like platinum to act as an electrode. Remember, we can't hook up an electrode, we can't hook up a wire to a gas or to a liquid, so we've always got to use a piece of metal. So we use a platinum, a very inert electrode to do this. So we can write it as a reduction reaction. So reduction is gain. So the hydrogen ions at a concentration of 1 mole per liter can gain electrons and can form hydrogen gas. And again, standard conditions, it would be 1 atmosphere. And we assign E standard for this reaction. So that's H plus H2. So the convention is to write the left-hand side and the right-hand side in order. So the thing that gets reduced and the thing that is oxidized like so. And we just assign that to a voltage of 0. So now if we build a cell like this, in cell notation, it's very nice, right? So what are we doing here? So at the very left and the very right, we've got the electrode, the thing we're hooking up a wire to. Obviously, the hydrogen electrode, right? We can't hook up a hydrogen to aqueous hydrogen or to gaseous hydrogen. There is a phase boundary between this liquid and the gas. And there's also a phase boundary between our electrode, that's a solid, and our liquid. And there's our salt bridge, and then our copper ion in the liquid phase, and our copper electrode in the solid phase. So we could calculate this cell voltage. And we're under standard conditions, so it's E cell standard. It is just the right-hand side electrode potential minus the left-hand side electrode potential. And the right-hand side electrode potential, so that is the copper electrode potential, minus the standard hydrogen electrode. And convention is that we set that to 0. So whatever we measure, we're essentially measuring the cell voltage as a way to measure the electrode potential. And when we do this, we actually get 0.34 volts. So we measure 0.34 volts, actually positive 0.34 volts. So that tells us that that electrode potential must be positive 0.34 volts. So that's really nice, right? So once you set one electrode to 0, you can just kind of bootstrap your way through the rest of the series. So you just can measure it against that one, and you know that that one contributes no voltage at all. So whatever you measure is whatever you get. So essentially what we've done is we've gone through the entire list of electrodes and compared them to the standard hydrogen one. And by doing that, we're measuring everything with respect to the same electrode, which we assign 0. In the same way that if we measure heights on the Earth, we typically measure with respect to, sea level. There's not really a big deal where we pick our reference point, because, for instance, if Portsmouth is 100 feet above sea level and Columbus is 300 feet above sea level, the difference between those 2 points is 300 minus 100, that's 200. If you measured from the center of the Earth, they'd still be 200 feet apart. I mean, the numbers would be much bigger, but when you subtracted, you get the same difference. So that's why it really doesn't matter too much where we assign the convention. So it's the relative differences that are important.